Welcome back to the Deep Dive. Today we're tackling something fundamental: impacts. Why is it that some collisions are, well, manageable, while others are just devastating?
It really comes down to the physics of motion, doesn't it? We're looking at instructional sources today, diving into momentum, impulse, and this really core idea of conservation.
Right, these concepts explain so much, from tiny particles to, I don't know, planets colliding.
Well, maybe not planets colliding, hopefully, but certainly how things interact. We're really aiming to unpack the link between force, time, and mass when things are moving. Think of it as impact management 101.
Okay, so our mission for this deep dive is get a solid grip on the main idea connecting these. Impulse equals the change in momentum. Let's start with momentum itself. All right, let's break it down. Momentum, we use the letter TIVN in physics. But what is it really? Like, what does it feel like?
That's a good way to put it. Momentum, Cav, is kind of like inertia in motion. Is how much something wants to keep moving the way it is.
Wants to keep moving. Okay,
Mathematically, it's pretty straightforward. Mass times velocity. So PP equals Uncle V, YOA. More mass or more speed means more momentum. Means it's harder to stop or turn.
and this applies across the board, right? Scale doesn't really matter.
Exactly. That's what's neat. You can have, say, a tiny, tiny bullet moving incredibly fast. Huge velocity gives it significant momentum.
Okay.
Or you could have a massive container ship moving almost imperceptibly slow. But because its mass is enormous, its momentum is also enormous.
Ah, right. So it's always that combination, the dollar times dollars. That's the measure of motion difficulty.
Ocean difficult or unwillingness to change, yeah. That product, more in Euler times V, is the key.
So if momentum P dollar is this measure of motion, what actually changes it? What do we call that?
That thing is impulse. Impulse is the push or pull over time that overcomes that momentum.
Okay, impulse. How's that defined?
Well, two ways that are linked. First, you can think of it as the force applied multiplied by how long you apply it. So text impulse is ogo do, force times time. Got it. But the really core definition, the one that connects everything, is the impulse momentum theorem.
Which states?
Simple but powerful. The impulse acting on an object equals the change in that object's momentum. So text impulse delta P2. That delta symbol just means change in.
Impulse equals change in momentum, delta P2.
Right. So if you want to change how something's moving its momentum, you need an impulse. You need a force acting for a certain time. And crucially, force and time are sort of tradable.
Okay, this is where it gets really practical, right?
Yeah.
Because if delta PT, the change in momentum needed, is fixed, like stopping a car.
Yeah, bring it from some speed down to zero.
Then that equation, Thutter pi delta P2, tells us something huge. If delta pig is constant, then Futtertown and Tyler must be inversely related.
Exactly. Increase the time in the force.
And the force goes down, dramatically sometimes.
This is the secret sauce for managing impacts safely. Anytime you want to absorb a big momentum change without breaking something, you stretch out the time.
Like catching a fast pitch in baseball. If your hand is just rigid, when?
Right. The time is super short. The force, $5, is massive. You're going to feel that. Probably break something.
So what do?
You learn to draw your hands back, right? As the ball hits, that little bit of give increases the contact time, $2.
Even just by a fraction of a second.
Even by a fraction of a second. That spreads the same total impulse, the same delta P over a longer duration. So the average force felt by your hands plummets. Makes all the difference.
But wait a second. If you increase the time, $2, doesn't the object, travel further while it's stopping? Why is reducing the force the main goal?
Excellent question. Yes, the stopping distance will increase. But think about what causes injury or breaks things. It's usually not the total impulse itself, but the peak force.
The peak force.
Yeah. Our bodies or car structures can handle a certain amount of energy transfer, but they break when the force gets too high, too fast. So safety engineering is almost always about minimizing that peak force, even if it means the stopping happens over a longer distance.
Which brings us to things like car safety features. The sources mentioned cushioning, seatbelts.
Crumple zones.
Right, crumple zones.
They're designed to deform, to crush. It looks bad, but that crushing takes time. It increases $2 during the crash.
So it sacrifices the front of the car.
To save the passengers by drastically lowering the peak force they experience. It's about spreading that impulse out. A rigid car would transfer that force almost instantly. Much more dangerous.
The flower pot example from the sources makes sense now, too. Falling onto concrete versus, say, soft ground.
Exactly. The concrete is rigid, $2 is tiny, $5 is huge. Crack. The soft ground deforms, dollars gets longer, $5 much smaller, Maybe the pot survives?
Duration is protection.
Fundamentally, yes. And you can flip it, of course, if you want maximum force, like someone breaking boards or bricks.
Ah, like that Alina Hookham example.
Right. You need to deliver the impulse in the shortest possible time. Maximize velocity, then stop it dead against the target. Minimize dollars to maximize $5. That's how you generate enough force to break things. So, time is the regulator, whether for safety or destruction. Now let's zoom out a bit to one of the truly fundamental laws of physics. Momentum conservation. This applies to what we call closed systems.
Closed systems.
Huh?
Meaning no external forces interfering, like out in space, or maybe just ignoring friction for a moment.
Pretty much. A system where the only significant forces are the ones inside the system between its parts. And for those systems, there's a beautiful rule.
Which is?
The total momentum of the entire system before something happens, a collision, an explosion, whatever, has to be exactly equal to the total momentum after it happens.
Before equals after. Always.
Always. For a closed system, think about standing still on a skateboard. Zero momentum, right?
Right.
Now you throw a heavy ball forward. The ball gets forward momentum to keep the total system momentum at zero.
I have to move backward on the skateboard. Recoil.
Exactly. The backward momentum you gain perfectly cancels out the forward momentum of the ball. The total stays zero. That's recoil in action.
Same reason a cannon kicks back when it fires a shell.
Precisely. The shell goes forward with momentum pair. The cannon recoils with momentum pao. The total change is zero.
And direction is obviously crucial here. Forward is positive, backward is negative.
Absolutely critical. Momentum is a vector. It has magnitude and direction. You have to account for that. If things are moving opposite ways, their momenta partially cancel out when you add them up.
Okay, let's use that fish example from the sources. A 5-kilogram fish swimming right at 1 meter. Momentum is 5 times 1, so 5 kilograms, positive 5.
Good. Now it swallows a little 1-kilogram fish that's just sitting there, stationary. Zero momentum for the little fish.
So the initial total momentum is just 5 plus 0 equals 5.
Right. After lunch, the total mass is now 5 plus 1 equals 6 kilograms. Conservation says the total momentum must still be 5.
So 6 kilograms times the new velocity must equal 5. The new velocity is 5 divided by 6, so 56 meters. It slows down a bit.
Perfect. Total momentum conserved. Now, what if that little 1-kilogram fish wasn't stationary? What if it was swimming left at 1 meters?
Vectors. Okay, the big fish is still plus 5 momentum. The little fish is 1 kilogram times minus 1 meter, so its momentum is minus 1 kilogram. So its momentum is minus 1 kilogram.
Exactly. So the total initial momentum is 5 plus minus 1, which equals 4 kilograms.
Okay, total momentum is 4. The combined mass is still 6 kilograms. So 6 times final velocity equals 4. Final velocity is 46, or 23 meters. Still moving right, but even slower now.
You got it. And you can see if that little fish were swimming left fast enough, say at 5 meters.
Its momentum would be minus 5. Then 5 plus minus 5, it'll weir. The initial momentum would be 0.
And the combined 6-kilogram fish would just stop dead in the water the moment it swallowed the smaller one. Momentum conserved.
Okay, so total momentum is always conserved in these closed systems, but collisions themselves can look really different. Sometimes things bounce off each other, sometimes they crumple, sometimes they stick together. How do we categorize those?
Yeah, the outcome depends on what happens to the energy, specifically the kinetic energy, during the collision. But remember, momentum is always conserved in all these types.
Always conserved. Got it. So what are the main types?
We usually talk about 3. First, the ideal case, elastic collisions.
Elastic. Like billiard balls, almost.
Pretty much the ideal model, yeah. Objects bounce off perfectly, no deformation, no heat generated, no sound. In a purely elastic collision, not only momentum, but also kinetic energy is conserved.
Okay, that's the perfect bounce. What's next?
The more realistic scenario, inelastic collisions. Here, some kinetic energy is lost.
How is it lost?
It gets converted into other forms, heat, sound, or, very often, into permanently deforming the objects. Think of 2 cars colliding and denting.
Right, the metal bends. Energy went into doing that. They might bounce apart still, but energy was lost.
Exactly. Momentum is still conserved, but kinetic energy isn't.
And the third type?
Completely inelastic collisions. This is where the objects stick together after impact and move as one combined mass.
Like the fish example.
Right.
Or maybe train cars coupling.
Perfect examples. This is where the maximum possible amount of kinetic energy is lost. Consistent with conserving momentum, of course. They become a single system.
Okay, elastic, inelastic, completely inelastic, that covers head-on stuff. But what about glancing blows or cars hitting at an angle like at an intersection?
Now we really need that vector nature of momentum again for collisions happening in two dimensions, say on a flat surface.
Like a T-bone crash, one car going north, one going east.
Exactly. You have to conserve momentum separately in both the north-south, let's call it Y direction, and the east-west X direction
Mm.
simultaneously.
Whoa, so you can't just add the speeds or something simple?
Definitely not. You have an initial momentum vector for the northbound car, all in the E direction, and an initial momentum vector for the eastbound car, all in the X direction.
Okay.
The total initial momentum is the vector sum of those two. If they stick together after the crash, completely inelastic, the final wreckage, the combined mass, will move off with that total momentum vector.
So if they had equal momentum magnitudes, one north, one east, the wreckage would move off exactly northeast.
Precisely, at an angle determined by those initial x and y momentum components. It's like finding the hypotenuse of a right triangle formed by the initial momenta.
That sounds complex to track in real life.
It absolutely is, but this vector conservation is fundamental. It's how particle physicists track what happens inside things like bubble chambers.
Bubble chambers.
Yeah, where they watch subatomic particles collide and decay, particles fly off in all sorts of directions. By measuring the final vector momenta of all the pieces and knowing momentum must be conserved, they can figure out the properties of the original particles and the interactions. It all comes back to conserving momentum component by component. Hashtag tag outro.
So wrapping this up, we've seen momentum, PMV$, and this measure of motion, and impulse, T and $, as the thing that changes it.
And the crucial link, impulse equals the change in momentum. Set a dot, 2 at the end dollar.
And the big takeaway, the practical magic, really, seems to be that inverse relationship. Control the time, T dollars, of an impact.
And you control the force, $5. Increase the time, decrease the force. That's the key to safety, to absorbing energy without destruction.
We went from simple definitions to vector conservation, governing everything from cannon recoil to complex car crashes.
Even down to those subatomic particle tracks. The underlying principle, conservation of momentum, holds true across all scales.
It really does. And we know rockets work by throwing mass backward to go forward, continuous conservation of momentum.
Which leads to a final thought for you, our listeners. Think about deep space. Asteroids, planets, they operate in an almost perfectly closed system, negligible external forces over long times.
Right, just gravity between them, mostly.
So if the total vector momentum of, say, our solar system or even a complex multi-star system must be conserved over potentially billions of years, how critical is understanding that precise vector conservation for planning any kind of long-term deep space navigation or predicting stability? Could it be the only way to ensure a probe or even a habitat remains on a safe trajectory over millennia, avoiding tiny but cumulative orbital changes?
Something to definitely think about. Join us next time for another deep dive.